Good morning. Let me continue lectures on geometric modeling, and today's topic is mappings. But first, I want to remind you that all materials of this course are available at the site you can see in this slide. Okay, let's start. How can one define shapes? There are several basic ways to do this. The first one is making a list of all elements, points of the point set. The second one, mapping from the known set. One more option is the point membership rule, and finally, with generation rule. The simplest way is to make a list of all elements of the point set by providing their coordinates. A linear array defines one point in n-dimensional space. For example, on the left, the list of two-dimensional points by their coordinates. In the middle, three-dimensional points. On the right, n-dimensional points. It is obvious that only finite point sets can be defined in this way, and no continuous shape, such as curve or surface, can be defined. Lists of points became popular with introduction of 3D scanners, lasers and others, generating point clouds on the object surface. These clouds serve as input data for object geometry reconstruction in different forms. By hand, we can introduce only a short set of points. Now, look please at this human brain and a squirrel, scanned by a laser scanner. Of course, it's also a finite list of points, but the number can be million points, which then help to increase the precision of the shape interpolation. Lists of points became popular in animation with introduction of particle systems, which are a cloud of moving points with predefined behavior used to model fire, smoke, water and other natural phenomena. These are examples of particle systems modeled as lists of time-dependent points with some attributes assigned for rendering purposes. We will study particle systems in more detail in the following lectures. The next way to define shape is mapping from a known set. If the set A is defined, mapping M establishes one-to-one correspondence between the set A and the new set B. Parametric curves, surfaces and volumes, presented later in this lecture, are defined in this way. Here you can see some examples of mappings. The first example is for 1D and 1D plus time. The second example is for two-dimensional space and two-dimensional space with time. There are examples of volumes. This example shows a volume rendered as a semi-transparent media with variable density in space. Here, volume defined by density is treated as a scalar field or explicit function of three variables, mathematically and in the process of visualization. There is no surface defined here at all. Here you can see frames of smoke animation. It is defined the same way as in the previous slide. It is also a density field of three variables, but now it's time varying. One of the simplest examples of defining shape using point coordinates is a unit cube in k-dimensional space, which is a set of points with all coordinates changing between 0 and 1. Here we can see one-dimensional cube, or a segment, two-dimensional cube, or a square, and three-dimensional cube. We have to distinguish dimension of space and dimension of shapes embedded in the space. Roughly speaking, shape dimension is the number of coordinates needed to specify a point in the object. The following definition is more formal. A shape is k-dimensional if there is a continuous one-to-one mapping of the k-dimensional cube or ball to this shape. The table below shows dimensions of the shapes in geometric spaces with n from 1 to 4. As we can see, dimension of shape can be equal or less than the dimension of space. A point is zero-dimensional mathematical object, which can be specified in any n-dimensional space using n coordinates. Curve is one-dimensional. Surface is two-dimensional. Solid is three-dimensional shape. We will also consider a special type of objects called volume, which is a three-dimensional object in four-dimensional space. Volume can be also called a happy surface in four-dimensional space. You can probably heard about the tesseract, not one of the six infinity stones, but a volume object which is the four-dimensional cube. This is an illustration of our informal definition of dimensions. You can see that one can define a curve in 2D as two functions of one variable. Therefore, its dimension is 1. At the bottom you can see the varying curve, which is defined as two functions of variables u and t. These are two examples in 3D space. You can see that the curve here is still one-dimensional object. This image shows that depending on the parametric equations, the shape of a parametric curve can be very complicated. A surface is a two-dimensional shape in space of any dimension. It means any surface pitch has one-to-one mapping to a unit square. This gives a ground to the parametric surface definition by mapping a unit square onto the surface pitch. In the shown example, our known set A is a unit square. The new set B is a parametric surface. The mapping M is given by a set of parametric equations for each coordinate x, y, z with the parameters u and v. By giving any arbitrary values from 0 to 1 to the parameters v and u, we substitute them to the parametric equations and calculate coordinates of the corresponding point on the surface. Thus, the entire square is mapped to the entire surface. This is an example of the parametric surface. Texture is used to show the mapping from the unit square. The grid on the surface is the mapped grid of the unit square. Here is an example of parametric definition of a surface changing in time. A solid is a three-dimensional shape in space of any dimension. It means any solid has one-to-one mapping to a unit cube. Parametric solid can be defined by mapping of a unit cube onto the solid. In this example, known original set A is a unit cube. The new set B is the solid. The mapping M is given by a set of parametric equations for each coordinate x, y, z with the parameters u, v, and w changing from 0 to 1. By giving any arbitrary values from 0 to 1 to the parameters u, v, and w, we substitute them to the parametric equations and calculate coordinates of the corresponding point in the solid. Thus, the entire cube is mapped to the entire solid. As we can see, the mapping procedure is quite similar for the one-dimensional, two-dimensional, and three-dimensional spaces, with only difference in additional dimension. Here we can see special form of parametric Coons solids mapped from a unit cubes. Because the original and final solids are embedded in 3D space, these both solids here demonstrate a simple deformation of a unit cube. Now we switch to the next approach of defining a set, point membership rule. A rule may be established which allows for any given point to judge if it belongs to the newly defined set or not. Implicit curves and surfaces and functionally defined solids and volumes are introduced in this way. Implicit curves and surfaces are defined using continuous function of 2 or 3 point coordinates respectively. For example, a set of points which function f of two variables x and y is equal to 0 defines an implicit curve, which is a boundary between two other sets of points on a plane. Inside points with positive function values and outside points with negative function values. Solids are defined with the inequality f at x sub 1, x sub 2, etc. x sub n greater or equals 0. Solids have dimensionality equal to the space dimension. Solids are n-dimensional objects in n-dimensional space as two-dimensional disk in the two-dimensional space, shown on this slide. Disk is a solid with internal and boundary points belonging to it. In this slide, you can see two examples of implicitly defined curves in 2D. Let us look now at object in three-dimensional space defined by function xi of three variables x, y, z. The point set with function values equal to 0 is an isovalued surface, or simply isosurface of this function. Usually, it's called implicit surface in computer graphics. It is just a slang, mathematically incorrect term. The simplest example is a sphere given by the following equation. Let us make a step one dimension higher and consider functions of point coordinates in three-dimensional space. The equation f equals 0 defines an implicit surface, and the inequality f greater or equals 0 defines a three-dimensional solid with the implicit surface as its boundary. Symmetrically to the two-dimensional case, the first equation in this slide defines an implicit surface called a sphere, and an inequality defines the sphere and all points inside, making an object called a solid ball, or simply a ball. Usually, implicit surfaces are associated with simple forms defined by quadratic polynomials such as a sphere, cylinder, cone, and others. This example shows a more complex surface defined by Chebyshev polynomial degree of 6. Here, discrete volume data, computer tomography data, are used also to define a function of three variables in the nodes of regular grid. Then, by making interpolation between the values in the nodes, we get a continuous function. At the last step, by defining the threshold value c, we introduce an isosurface or implicit surface f of three variables equals to c. Finally, we discuss a generation rule as the way to define a shape. A rule can be specified to generate a shape in a recursive manner, starting with some initial shape, usually very simple, and use the current shape as input at the following generation step. In this way, fractals, L-systems, and other procedural models can be defined. We introduce here an iterative function p' in two-dimensional and three-dimensional spaces. The method usually starts with the point and generates a new point, and then is applied recursively. The final point set is the collection of some generated points selected by given constraints. Here you can see an animation produced by this method. In the case of Lindemeyer systems, the shape generation starts from one or two simple shapes. This initial shape is assigned to some symbol called axiom, and then some formal grammar is introduced by giving substitution rules for all involved symbols. For example, x can be small lowest segment of the tree, and f can be one leaf. Then the rules are applied iteratively to the current shape. These are some good phrases to remember. Geometry is the mathematical science of shape. This fact leads to the mathematical pun: without geometry, life is pointless. This is our main textbook where several chapters deal with geometric modeling. Additional references are shown in the next slide. Unfortunately, there is no single source where you can find information on this lecture. Here is the list of additional references used to prepare this lecture.